Thank you for doing this interview with me today. Just to
Yeah,
introduce myself, my name is Annie, and I create Sustainability Beyond the Lab to make sustainable research more accessible for general audiences, as well as showcase the barriers of why these sustainable technologies aren't scaled up. Um, so to begin, could you also introduce yourself and then tell us a little bit about your work as director of the Nuclear Science User Facilities at Idaho?
great. Yes, thank you for inviting me to this interview. I'm Brenden Heidrich. I'm the director of the Nuclear Science User Facilities. We're a user facility like 29 other at the Department of Energy, but we're focused on nuclear energy work, particularly uh, the what we call the radiation effects on nuclear fuels and materials, the
Mhm.
things that make up the nuclear reactor. Uh, we want to basically run them through their whole lifetime before they actually ever go into a reactor and ensure that they'll maintain their strength, their durability, and so on during the whole life of a reactor, which used to be 40 years and
Mhm.
is now 60, 80, maybe 100 years. Uh, so we have the responsibility of doing that work. And what we do as a user facility is invite people to bring their research in. We really don't do any of our own. And then we match them up with the people and the research capabilities to carry their work out, and then we pay for that. I
Mhm.
mean, well, the Department of Energy pays for it. We're just the conduit
Yeah.
that makes contact with the researchers.
Mhm. For people who might not be familiar with nuclear energy or
Sure.
advancements in reactors, what are important challenges that nuclear energy research aims to address?
Well, like I said, these materials, and they're typically sort of common materials that you might be aware. Steel is what makes up a lot of the vessel. Now there's 100 kinds of steel,
Mhm.
but really what we use in the 94 reactors that are running around in the U.S. making power are really grades of steel that we've been using for, I think, probably 70 or 80 years.
Mhm.
The difference is that in a nuclear reactor, some of that radiation that's given off actually can damage the material. Now, it happens very slowly, so it's not something that would occur in any case over days or weeks or years, but over tens of years, that material can degrade. Now,
Mhm.
it's still really, really good, but we want to make sure that in all cases, not just normal operation, but if there's an accident like at Fukushima, where the cooling was removed from the reactor for a period of time, that if it goes up in temperature, our material is still good. Or if there's really any other kind of change off the normal operation, we know it's good for the normal operation. We want to make sure it's good for everything.
Yeah.
And now, with all these advanced technologies that are coming out, uh, the reactors that we've run for 70 years or so are just one part of the equation. There's new ones that'll run at higher temperatures to be more efficient,
Mhm.
maybe have different coolants. We use water because we know a lot about water. It's we understand it. It's not probably as efficient as some of these other technologies, so we're looking at things like liquid sodium or what they call molten salts, which have been used for years to transfer heat in like solar thermal energy systems.
Mhm.
We want to look at that for nuclear, and they'll have different. They may corrode the material differently than water does.
Mhm.
They may interact differently under irradiation again. So these are all things. Anytime we bring a new material into a nuclear system, we need to test it, or we should test it, and that's kind of what we do.
Yeah. What kind of exciting projects have you worked on recently or in the past?
Well, exciting to me is maybe not exciting to all of your viewers. But a lot of what we do is fundamental science.
Mhm.
So we work with I'm pointing as if you can see our big data center next to me, but
Mhm.
our computational folks, uh, where we produce essentially experimental data.
Mhm.
They have software that basically simulates all of the reactor systems,
Oh.
whether in a variety of different ways. And then we try to benchmark the two of them together. So we've done some experiments specifically designed for that. often you end up not really head on, not really matching apple for apple. And we've had some work that was specifically designed for that because, you know, for these 70 years or so, the people that regulate the safety of nuclear reactors have really relied on experimental data.
Mhm.
And that's kind of hard to come by. It's expensive.
Yeah.
One of our big projects can cost several $1 million and take really up to 10 years to do.
Mhm.
And that's a really slow way when we've got advanced manufacturing, 3D printing of materials, and they're just coming up with new materials all the time, new ways to do it. Now with AI, where we were sort of marching through all of these simulations really at light speed,
Mhm.
but we're still generating experimental data at really human speed,
Yeah.
which is a great way to work, but it's slow in compared to how the other tools now are. So we're doing a lot of work, well, at least starting to do a lot of work with the AI teams and the simulation teams to try to take the data that we've made over the 20 years NSUF has been around, but really over the about 70 years that INL or its predecessors have been around,
Mhm.
and train AI models to help us find gaps, to find where our money would be best spent to fill in those gaps, to inform the models, to hopefully do a lot of this, supplement the work that we do with new AI tools to help drive the this new reactor development.
Mhm.
So really, I think the implementation of AI and advanced manufacturing has been probably the most exciting amount of work
Yeah.
that we've done, and we're hoping to see some benefits from that.
Mhm. Yeah. AI and modeling sounds like a very like useful tool. Like as you mentioned, it's much quicker, honestly.
It's just a matter of really sort of grounding it in reality,
Mhm.
which is this experimental data.
Yeah.
Uh,
A major part of your work, as you mentioned, is how nuclear models or nuclear materials respond to irradiation. What happens to materials when they're exposed to like intense radiation inside of a reactor? And why is understanding that behavior so important?
so primarily, what happens? It's a really good question because it's
Mhm.
not something that I like to talk about nuclear problems in a non-nuclear world.
Mhm.
So nuclear energy is an important part of the energy mix, but these nuclear materials and the study of them is this tiny wedge of material science.
Mhm.
So if I need to buy a thermocouple, say, to measure the temperature in a reactor experiment, everybody, except a few of us that use thermocouples, don't even consider how irradiation will affect that device,
Mhm.
but it does. So so the irradiation we care about really is in two kinds: neutrons and gammas.
Mhm.
Uh, Both of them come from the fission reaction in a nuclear power plant. We shield people and the environment from both of them, but they interact with matter in a very different way. So gammas will do a lot of damage to things that are essentially chemically bound.
Mhm.
So if you have polymers, plastics in their people, we keep the people out, obviously, uh, or I mean even things like paint, anything that's really sort of put together, essentially sort of like a bullet.
Oh, I think you might have cut out a little bit at the end there.
Oh yeah, sorry, the internet's being a little bit funky.
Yeah. Um,
So
you,
go ahead.
last thing I heard was kind of like about paint and things
So
can.
gamma radiation
Mhm.
really affects things that are like sort of that are the chemical bonds are important for
Mhm.
things like paints, polymers, the insulation in cables, uh, and so we've done some testing on that. We actually just finished a big project on looking at seismic dampers for
Mhm.
power plants. So these are, well, I'm showing you here with my hands.
Yeah.
The ones we tested were sort of about basketball sized,
Yeah.
but for a reactor, they would be, sort of car-sized things. But they
Mhm.
do have polymers in them, and they're used for seismic or vibration damping in a whole variety of industries. But to really good results. But now in nuclear, where you'd have radiation, now you have to look at the radiation effect on those polymers, and it's been all good news. So I'll let the researcher talk about his results, but it'll actually be up on our website.
Yeah.
Uh, and yeah, because it's actually worked out really well. But most of the work we do is for the neutron radiation. And the neutron radiation actually sort of acts like bullets in material. It has no charge to it, so it's not really slowed down by other things. But it does go in, and it'll hit an atom.
Mhm.
And if it's got enough energy, it'll knock that atom out of its crystal structure. We think of crystals as being things like diamonds or
Mhm.
quartz or something you see. Well, most material is actually in a crystalline form. Most metals are. Uh, so it knocks it out of that line, and the crystal structure gives it its strength,
Mhm.
a lot of its other properties. So it knocks that atom out. Now that atom does have a charge,
Yeah.
or the nucleus of the atom does have a charge when it's knocked out, which then can cause what we call a cascade, which can knock more atoms out of its lattice. And then you get some damage.
Yeah.
And one neutron is obviously trivial, but when you have trillions and trillions of neutrons over years, decades of time, now you can cause some damage.
Yeah.
And that can cause voids in the material. Like I said, you have this beautiful crystal structure. Now you knock things out. Maybe something else goes into its place. Maybe
Mhm.
it doesn't. You might get swelling because of that. A whole variety of changes can happen. And in almost all cases, it makes the material worse.
Mhm.
Weaker in some cases. Like I said, it can change dimensions by swelling. Uh, and all of these things, I guess, when they do the initial safety evaluation, they look at the material basically as it was when it was built. But since that's not how the reactor is going to be,
Yeah.
they also have to look at it over time. What does it look like if it's been irradiated for 40 years? Like I said, or 60 or 80 or even 100. And the way they get that data is either through what we call irradiation testing,
Mhm.
uh, running these materials in a test reactor like the advanced test reactor at Idaho here, or you can harvest materials from power plants that have been running for a long time.
Uh-huh.
So that's very important data to have because that's the actual materials in the actual conditions. But that doesn't exist for the advanced reactors we're trying to build now.
Mhm.
So instead, we use modeling and simulation, like
Yeah.
we have next door, and irradiation testing to get some of that data.
Mhm.
It's actually really hard to get all the data we need because these new reactors, uh, because they're trying to be more efficient and safer and have different coolants and things. Like I said, the really cool thing about the non-water reactors, the molten salt and the sodium, is those materials, those liquids don't boil in the reactor.
Mhm.
So we can't have a Fukushima type or a 3 Mile Island type problem
Yeah.
because, like I said, it stays liquid a long time. But because of that, like I said, we have different interactions. And so we'll be operating at higher temperatures to get higher thermal efficiency, uh, to get longer, better use of the fuel that we put in the reactor.
Mhm.
In fact, in some cases, actually, there are designs to put used fuel that would normally be, well, maybe put in the ground back into a reactor, a different type of reactor, to
Mhm.
run that longer. And so we do the irradiation testing with the modeling and simulation to basically see what we think that material is going to look like at the end of its life, whether that's 40 years, or in the case of fuel, it might just be a few years in the reactor. And then that data needs to go into the safety evaluations.
Yeah.
Uh, so essentially, we're working with researchers, universities, other national labs, companies in the nuclear industry to help them get the data they need to both design the new reactors and to evaluate their safety.
Yeah. What are some of the biggest challenges in like scaling up nuclear energy, um, for like practical deployment?
So that's a very easy question. It's been the same answer for a long time, and that's
Uh-huh.
cost. The current fleet of reactors that we have, what we call light water reactors, because they use water as a coolant. That's sort of the main difference in the technology. Like I said, we understand water, it's great. But it's not terribly efficient. It's about 33% efficient.
Mhm.
So a reactor that puts out 1,000 megawatts of electricity makes another 2,000 megawatts of heat
Mhm.
that needs to go somewhere. So
Mhm.
we need these big cooling towers. The light water reactors tend to be somewhat large. So we have these big concrete containment buildings.
Yeah.
That sort of the cooling towers and the containment domes are sort of the symbol you think about when you think about what a nuclear power plant looks like. So they're expensive.
Mhm.
They're not bad. They're really producing about 20% of the US's electricity
Mhm.
and more than I don't know what the number is now, 50, 60, 70% of the carbon free or low carbon electricity. But they're big. And that costs a lot of concrete and steel, and that costs
Mhm.
a lot of money.
Yeah.
So one of these plants could easily cost, $8 billion or so. And boy, that's a lot.
Yeah.
So it's a matter of really the big upfront cost. If you're
Mhm.
going to build a nuclear power plant, like I said, say maybe it's $8 billion for 1,000 megawatts of electricity. Well, things like natural gas plant has a whole lot less infrastructure. So maybe a natural gas 1,000 megawatts costs you $500 million, maybe 1/16th of the cost. Now there's more cost over time, and then certainly with respect to sustainability,
Mhm.
if you look at that whole life cycle, and you bring in those externalities, as we call them, of adding carbon to the atmosphere,
Yeah.
in the case of a coal plant, particulate pollution that actually, not to get too dramatic, but people die, from high particulate in the atmosphere. The U.S. is generally really good about that, but we can see the effect of the way it was before we had a lot of these stack scrubbers in coal plants.
Mhm.
So it can be easy for a utility or a government to say, boy, we really don't want to spend $8 billion, even though we believe that long term, over the life of that plant, it's a really good deal. Well, we'll spend, a small fraction of that and build some gas. No
Mhm.
one's building coal plants
Mhm.
anymore, but you know, so one of the things that we've been looking at, we being the whole nuclear energy enterprise, is how to bring that cost down.
Mhm.
And one of the potential solutions is what we call microreactors.
Mhm.
And it was small modular reactor sort of goes along with that too. Uh, the other problem is if you need to build an $8 billion power plant, you need to take a lot of that money as a loan up front.
Mhm.
So small modular reactors came along and they said, well, great, we're going to build 1,000 megawatts, but we're going to do it in maybe 8 or 12 units. And they won't take, say, 10 years to come online. They'll come online at maybe 3 years, 4 years, 5 years, 6 years till we get all 10 of them. And we'll be able to make money because we'll bring those first small plants online earlier in the process. Microreactors goes another step farther. And instead of maybe, say, 12 units adding up to 1,000 megawatts, now they're much smaller and it might take something like 50 to add up to that. And we probably wouldn't build 50 as one big site,
Mhm.
but you can put them closer to the need. So maybe a steel foundry needs 50 megawatts of electricity. Well, it
Mhm.
could build a couple microreactors. Or the other really good synergy is AI data centers. Uh, so there's a really good uh, uh, matching the technology to the technology need.
Mhm.
Where the other problem is if you may say, well, we need some more electricity in wherever you happen to live.
Mhm.
Do you need 1,000 megawatts? Well, maybe not. Generally, with the way communities grow, they don't take these big step changes. So you say, well, we need some. So well, you could bring on a small gas plant, or you could also add if the climate and the area is right, you can bring on wind turbines, solar panels, maybe tidal, if it's that area. But if nuclear is your need, then we have these new, basically sort of right-sized reactors, that can fit into that. And a hospital could have a reactor, to provide backup power. Like I said, data centers are really sort of just perfectly fit for
Yeah.
this technology. Uh, but yeah, getting over that cost barrier,
Mhm.
uh, generally nuclear is really efficient. So if you own a nuclear power plant and you're just basically paying to run it, you're probably in really good shape because if it's running well, it's really inexpensive to run.
Mhm.
It's just that building the new one, boy,
Yeah.
that's a big hurdle. And so we're trying to come up with ways
Yeah.
to address that.
Mhm. It's really interesting hearing how like smaller reactors can kind of cut back that initial cost, and how it can literally be integrated with these like hospitals and data centers.
The other real big challenge was the number of people that have to work at these plants.
Mhm.
Uh, and some of that's the security force, the operations team is generally pretty large.
Yeah.
Some other technologies that they're looking at for these small reactors is like either remote or autonomous control.
Mm.
So people are really good at lots of things. What we're not really good at is looking at, if you've ever seen a picture of a control room, it's just hundreds of gauges and dials. Uh, we're not really good at looking at that and sort of pulling all that data into our brain and making decisions based on it. We can, obviously we can do it. We can fly airplanes, we can run nuclear power plants, but those people are trained for years and years and years to do that.
Mhm.
What we have that's really good at taking a lot of data in sort of assimilating it and making decisions are computers.
Mhm.
And that definitely makes people nervous. And I don't think we'd ever really have plants that didn't have a human, as they say, a human in the loop,
Mhm.
as sort of the final decision maker. But, if you could take say a 20 megawatt microreactor and pair it with maybe, a couple dozen other ones, all that operations data goes into a computer. There's someone there watching it.
Mhm.
It's already considerably simpler design. So there's fewer things to watch. And it just runs as what I've heard some people call almost a nuclear battery.
Mhm.
Uh, and you don't even necessarily, uh, one of the things that also is time and money consuming is every couple of years or so, you have to refuel the big power plants. So it shuts down for a month or so. It used to be several months long. The operations teams have gotten really, really good. And it's now about a month.
Mhm.
But they sort of disassemble some of the reactor, pull some of the fuel out, put new fuel in. And that requires, like I said, some time, some cost to it. Usually a special crew comes in to help with that because it's pretty complex.
Mhm.
For some of these microreactors, you don't refuel them. They run for 5 or 10 years, and then the company comes, picks them up, takes them back to a factory where they're refueled in for one spot, and they give you a new one. A new one might come on the truck. They take the old one away, and then they service it, refuel it. So you as a consumer or as a utility, they don't have to deal with that stuff.
Yeah.
It's uh, it's really sort of you're almost buying electricity as a service.
Yeah.
Because, if you're, a utility, you don't really care about a reactor. You just want electricity that's probably inexpensive and reliable for all your customers. And like I said, so some of these new technologies can be really good at trying to provide that.
Mhm. Yeah. What role do national labs such as Idaho National Laboratory play in like bridging the gap between fundamental studying and then actual deployment?
Wow. So really good question. And really one that was at the base of the creation of the national laboratories.
Mhm.
So I can show you a picture, but we used to have this graphic we called the valleys of death.
Yeah.
Okay, so you
Mhm.
and so it companies, industry is really good at deploying technology.
Mhm.
Universities are really good at creating it, coming up with ideas, uh, some of which are bad and go away. but some of which are really good,
Hmm.
but they don't. Now, some of them are building these sort of technology parks right by the university to sort of develop some of these technologies. But that's where, at least in some cases, and certainly in nuclear, the national labs can step in. And they're generally big government installations and big investments in research infrastructure.
Hmm.
So INL here is the only dedicated nuclear energy national laboratory, although a bunch of other laboratories do nuclear energy work.
Hmm.
The Department of Energy Office of Science has a bunch of national laboratories that are really dedicated to a whole variety of missions, but generally sort of fundamental science.
Hmm.
And that was one of the reasons that Idaho National Laboratory and the nuclear science user facilities came about. Because while we do a lot of that fundamental science, we
Hmm.
really started to sort of do what they called applied engineering. We knew a lot about this technology. We just really needed sort of some test beds and some laboratories to kind of develop it. Back then, we didn't really care about coming up with some new scientific theory. We wanted to figure out what was the best fuel for these new reactors. Now everybody's much more broadly scoped, and we do a lot of fundamental science here too. But the labs were here for, like I said, these big investments that we couldn't really expect anyone else to come up with.
Hmm.
Uh, they actually grew initially out of the Manhattan Project to develop the atomic bomb, and thankfully, there's a couple laboratories that still do that sort of security work,
Hmm.
but most of the other laboratories now are really here for really sort of the benefit of mankind, generating scientific data. And then user facilities were really intended to be the gateway for non-lab people into the laboratories. So when we started, like I said, almost 20 years ago, we had the advanced test reactor and some other capabilities here, but it was really hard for anybody else to come and get access to it,
Hmm.
just because it was expensive and you really kind of had to know somebody to even really get involved with it. So the user facilities sort of democratized this big science. You can come in with, in the case of nuclear science user facilities, two-page proposal, and you can get one of what we call our rapid turnaround experiments, about 2 to 4 weeks worth of time in one of our laboratories to solve a particular problem. Whereas if you had to pay for that, it would obviously
Yeah.
cost money, and you'd still have to, write the contract to get in here, and you'd probably still kind of have to know somebody.
Hmm.
You know, NSUF and the other user facilities kind of break down those barriers.
Yeah.
And there are thousands and thousands of researchers that use the U.S. user facilities for different research projects every year.
Hmm. Yeah. Before we wrap up, is there anything that you think that the public or like policymakers or scientists should know about nuclear energy?
So we used to say nuclear is the technology of last resort,
Hmm.
and that sounds horrible, but it's because it is somewhat complex.
Hmm.
You know, uh, some people on our side uh, don't necessarily like wind and solar, but boy, that solar in particular is elegant. You can really sort of put this thing out there
Yeah.
and you could just get electricity from the box. Uh, but that doesn't really solve all our problems.
Mhm.
Yeah, wind is the same way. It just sort of operates a little bit differently. You come to nuclear so when whatever you need, and it could be even, nuclear medicine saves tens of thousands of lives, and I'm probably underestimating that every year. But you don't do nuclear medicine if you can do something else.
Mhm.
Uh, so basically, nuclear brings a lot to the table, and you pay for that with the complexity and in some ways the cost. Although, like I said, we're doing a lot better on the cost.
Mhm.
I guess probably the thing to really emphasize is there are experts out there, and if you have questions, ask. So things like your website, your YouTube channel are really a great way for people to demystify some of this stuff.
Yeah.
Because sometimes people say, yeah, nuclear, I at least feel how complex that is. I
Mhm.
know it's a little dangerous, or it can be. So I can't understand it, so I'm just going to move on. Well,
Yeah.
you can, and like I said, we're here to help. Really, that's what the national labs are here to help. There are good organizations like the American Nuclear Society,
Hmm.
professional organization. There's the Health Physics Society for the essentially the radiation effects on people and animals and the environment. I just said ask. You
Hmm.
know, if you were interested in doing some research, the number one thing we tell our users, contact us. All
Yeah.
our information's on the website. That's what we're here for.
Yeah.
And we can help to, turn your idea, your question into a project for us. Uh, we have, people that do outreach here at the laboratory, that will come and speak, with a lot of materials. It is complex, it's challenging, but we think it's worth it.
Yeah. Yeah. Thank you so much for sharing both your research and in your perspective. I found that really interesting, especially hearing about like making smaller nuclear reactors. That's something that I personally have like never thought of while looking into nuclear energy.
It's a huge real paradigm shift because we
Mhm.
got bigger and bigger and bigger. Because
Yeah.
there are some really good benefits to making really big reactors,
Mhm.
but they come with that really big price
Yeah.
tag. So, well, could we go in? And that's really the brainchild of our current laboratory director, Dr. John Wagner,
Mhm.
was getting into this new idea. So yeah, like I said, there's a lot going on. Uh, I will tell you, so I was professor for a number of years back at Pennsylvania State University.
Uh-huh.
And with great students, and I was a student myself. The enthusiasm of the current crop of students is amazing. Students will end up going to state capitals to not protest, to I guess lobby for changes. A lot of states had nuclear bans,
Mhm.
you know, and so you'll see students there, lobbying their local congressman for things like this, doing outreach to K through 12 schools.
Yeah.
It's really kind of inspiring to see people other than stodgy old people in ties sitting in offices interested in nuclear. So I think the younger generation, the current generation is a lot more interested in the ability for nuclear power to,
Mhm.
solve the environmental issues, the challenges that we're working with.
Yeah. Yeah, thank you again. It was a
Sure.
pleasure to interview you.
Yeah, like I said, really happy to do this sort of thing, and said appreciate having these outreach channels yourself. Uh, you can provide my contact information. It's on the
Yeah.
website, and I'm happy to answer questions from anybody in your audience.